maybe. Is it working? Oh, it's thinking. Hey, there we go. All right. So we started looking at the different types of acid-base reactions that we can have. And we started with strong acid, strong base reactions. Okay, so we did a couple examples of that. Somewhere in here. There we are. We started with the net ionic equation of strong acid, strong base, and then we used that to do an a mine table with a strong acid, strong base reaction. And the whole goal here was to solve for pH. Okay, so strong acid, strong base, you mix them together, something happens, they neutralize one another. What's the pH when it's all done? Okay, and in this instance, we had excess strong base, so we used that to solve for pOH, and then we solved for the pH from there. In this one, in order to set up our mine table, we needed to get to moles. Okay, so a mine table is a second type of organizational tool that I'm kind of giving you, and it's for neutralization. In other words, it's for acid-base reactions. And when we use these, we have to insert moles for the initial, not molarity. So in this problem, you were given volumes and molarities, and we had to convert these to moles first prior to setting up our mine table. So we did a little bit of factor label. We found our moles of acid, we found our moles of base, and then we set up the table. In this instance, we had equal moles of acid and base. When acids and bases react, they react until something runs out. And in this instance, it was equivalent. So what did we have when we were all done? We had water, and we had some salt. The salt was magnesium nitrate, which is a neutral salt. So our pH was just 7. We didn't calculate it per se. We just kind of analyzed the situation when we were all done and realized that if we just have water and we just have this salt that's neutral, well, then we're at a pH of 7. We're good. We then moved on to a strong acid, weak base reaction. And in this instance, we reacted our strong acid and our weak base, and we had excess strong acid. And when we were all done with this neutralization, we came to the conclusion that we have strong acid and we have weak acid. And then I made the argument at the tail end of the hour yesterday that this one's going to really affect the pH way more than this one is, right? Okay. This is going to end up being like a tiny little plus X that we would more or less ignore anyway. So when we have strong acid and weak acid in the same solution, it's the strong acid that's really going to determine our pH. So we acknowledged what we had for the strong, we ignored what we had for the weak, and we solved for the pH this way. Onward and upward. Weak acid, strong base. Now, this is more or less the same. We're just switching which was weak and which was strong, right? The previous example was a strong acid, weak base. Now we're doing the opposite. What's the generic net ionic equation for this? Well, I have a weak acid. When something's weak, what does that mean? It doesn't dissociate. So I'm going to write my weak acid generically as HA. A is some anion, something, right? We'll fill that in later when we get an actual example. But our acid's going to be together, not H1 plus and A1 minus dissociated, because it's not strong. It's weak, so it stays together. So we're just going to write this as HA. This is aqueous. And then we're going to add that to a strong base. What symbol do you want to use for strong base? I like that for weak base. What was a strong base in our strong net ionic? Here's my net ionic for strong. OH1 minus. When you have a strong acid or a strong base, it breaks apart. If it's a strong acid, the only part that we care about is the H1 plus. If it's a strong base, the only part we care about is the OH1 minus. So our reaction here is going to be HA, weak acid, plus hydroxide, which is our strong base. And then when these react, what are we going to get? Bronsted Lowry. We're going to get water because this acid is going to donate to the base. We're going to get A1 minus. Hey, Mr. Sekar, what can we do for you? Uh-oh. Me?
Anybody nervous? Better? Oh. Really? Okay. I just need you for a second.
You're good, you're good. If you want to hang out, you're more than welcome to hang out. You know, some pre-spring break acid base.
It's early to me.
Is it?
Yeah.
Thanks, guys. I appreciate that. I was waiting for you to throw me under the bus. I will. Okay, whoops, now I'm distracted. Hold on. H2O plus A1 minus. This is a liquid, this is aqueous. So this is the generic setup for weak acid, strong base. Let's look at a real example. If a solution contains 0.5 molar acetic acid, which is HC2H3O2, and 0.6 molar sodium hydroxide, what is the pH of the resulting solution? Same thinking, same thought process as what we did at the tail end of yesterday's class. We need to get to moles first. We're going to set up a mine table, and we need moles if we're going to set that up. So let's take what we have right now, okay, and let's get to moles. Oh, wait. Did I give you a volume? No. So let's assume it's 1. Let's just make life easy. Let's assume we have 1 liter. Okay? So we don't have to do factor label this time. Now, if I give you volumes, then there's no assuming, right? No assumption can be made. If I give you volume, you have to do the appropriate factor label to get to where you need to go. So we're good here. That's nice. We can go straight to the mine table. Let's set this thing up. I want a reaction. I always want a reaction above my table because then I can reference which is what. So let's make sure we get that down. I have a weak acid. I have a strong base. When these react, I will get A1 minus. Now, in this instance, A is that whole thing, right? It's an anion. And my anion is acetate. So I have C2H3O2 1 minus, and I have water. Okay, we can start filling this in. I have 0.5 moles of acid. I have 0.6 moles of base. I didn't make any of this product yet, so that's 0. And water, who cares? What was that? Oh. Yeah. Not in this problem. In the world it matters, but wow. Well, no, it matters. It's not here. Acid, base, what do? They neutralize until something's gone. So we will react these and neutralize these until something runs out. The acid is less, we're going to run out of acid. Now, this is a product. We're going to make some of that. And it's a 1-to-1-to-1 ratio, so we're going to get 0.5 moles of acetate produced. At the end, not equilibrium, at the end, I'm going to be left with 0.1 moles of excess base, and I'm going to have 0.5 moles of this. Hey, what is that? What was that? It is my conjugate base. That is exactly what I'm looking for. This is the acid. When I remove a hydrogen from it and I produce this, that is the conjugate base of this acid. Strong or weak? Strong or weak? Remember, weak's the middle ground, right? This is a weak acid, therefore its conjugate base is also weak. Okay, so what do I have in my solution? I have strong base and weak base. Which one of those is going to affect the pH to a greater extent? The strong base. So much like yesterday when we ignored the weak acid that was in our solution, right now we're going to ignore the weak base. We're just going to assume that it's just not going to affect the pH that much, at least comparatively. If we have excess strong base, this is going to do way more to our pH than this will. In order to solve for how much this would affect the pH, we would have to set up an ice table, we'd have to solve for X, and then we would add that little value of X to this value of hydroxide. And I'm telling you, it wouldn't hardly affect this value at all. Whether or not we add in this contribution, we're pretty much going to get 0.100 molar for the hydroxide. So let's ignore it. Let's make life easy. Unless you want to do an ice table. Guys, there was a hesitation there. We will later today. Hold on.
Let's go.
Now, what the heck's this? Right? What is this? This is my molarity of hydroxide. I want to solve for the pH of this solution, right? Now, in reality, this is moles, but we made an assumption that it's 1 liter, so we're good. Okay? So it's also 0.1 molar. I want to get the pH. What should I do? Let's take the negative log of this. What will that get me? If I take the negative log of that, I get the POH. What do you get for a value of POH if somebody's working ahead? Say that again? Oh yeah, I suppose I could figure that out. 14 minus 1. There we go. Make sense? Cool. All right, let's get a little spicier. Eventually. Okay. Weak acid, weak base. What is the net ionic equation for a weak acid, weak base reaction? We're going to use HA for our weak acid. We're going to use B for our weak base. Bronsted-Lowry. What's going to happen? Stays together, stays together. This has no OH anyway, right? Bronsted-Lowry reaction. The hydrogen is going to transfer. In other words, Bronsted-Lowry acid-base reactions are proton transfers. And every now and then, AP likes to drop that phrase. Look at the following proton transfer reaction. And then your brain goes, whoa, 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 time out. I don't know what the heck that is. But if they had said acid-base, you'd be like, oh, okay, that's easy. I know what that is. So careful. They can phrase things just in that slight annoying way to throw you off your game. Proton transfer is a Bronsted-Lowry acid-base reaction because we are transferring a hydrogen ion, and a hydrogen ion is a proton. So it's a proton transfer. All right, so what do we get? We get A1 minus, oops, not a plus, my bad. And we get HB 1 plus. This is the generic setup for weak acid, weak base. Now, we're not going to do math with this. Because kind of like I said yesterday, the problem is if I do math with this, then I have like multiple competing equilibria at the same time, which would require multiple ice tables, multiple K values, and then we'd have to make a comparison between our K values and our, Yeah, let's not. We're not going to do that. But you should be able to do this. If I gave you a random weak acid, like with a real formula, and I gave you a random weak base with a real formula, you should totally be able to give me the reaction for it. All you need to do is move one hydrogen from the acid over to the base. That's totally fair game. Okay? So the reaction is fair game. The math we're going to ignore. Note that all of these examples so far, after the acid-base reaction has occurred, we're left with excess of the strong species. In the first type of problem we did, it was strong, strong, and we had extra strong when it was all done, right? I think the second problem, we had equal molar, so then we were just left with water and, salt. But when I did my two other examples, I had strong acid, weak base. I had excess strong acid in that problem. Then we did weak acid, strong base, and I had excess strong base in that problem. Every single problem we've done so far on this worksheet is we've had extra strong substance. What if we're left with extra weak substance? Or what if we have equal amounts of weak acid and strong base? Well, then it gets more fun. This is rhetorical, by the way, my questioning. I'm just getting your brains thinking. Let's do this for real. This requires some, this is like, it requires both conceptual thought and mathematical process, which is just, good stuff. That's not what I said. No, it'll be fine. When I do it, it'll make sense. And then if I leave you by your lonesome, you might struggle a smidge, but we'll get there. Determine the pH when 0.5 moles of each HClO and KOH are mixed together in a 1 liter solution. All right, still being nice with the volume. That's good. Okay. I have HClO and I have KOH. Strong or weak? Yes, it is weak. How do you know that? It's not one of the strong ones. Yes, if you look at the list, that's how you determine it. That's rather dumb. Okay, and I ask you that every time I say this, right? Like, how many times have I said that this year? At least 4. That's a fair assessment. Okay, but your answer should be the same. You got to memorize those 6 basically. The 6 are HCl, HBr, HI, HNO3, HClO4, which is perchloric, oh man, nope, said that one. HCl, HBr, HI, H2SO4. That is the last one. We've got 6. HCl, HI, HBr, HNO3, HClO4, and H2SO4. It's not one of those. It's weak. Hey, look at that. It's not one of those. It's weak. Okay. This, KOH, strong or weak? It is. So what does that mean? Correct. So we have a weak acid and a strong base reaction. Let's write out the net ionic equation for that process. The acid is going to stay together, meaning whatever the formula is, it is. This is a weak acid. It will stay together, undissociated in our process or in our step or in our reaction. The other thing is a strong base. This is going to dissociate completely. When your strong base dissociates, we don't really care about the cation. Much like if we have a strong acid and that dissociates, we don't care about the anion. The only part we really care about there is the hydroxide. So I'm going to end up with my weak acid plus my strong base yielding, after I transfer the proton, right? I'm going to get ClO1 minus plus H2O. This is called hypochlorous acid, and this is called hypochlorite. Sure you care? Excellent. I'm glad I shared that with you then. Oh, it is. I'm sorry. Yep. Yeah, it's always a liquid. This is solution chemistry, acid-base chemistry. So yes, our water is going to be a liquid. Sure. So like if we're combustion, so like there's reactions where if we release a whole bunch of energy, right, it might get hot enough where the water turns into a vapor. So yes, when you burn things and you produce water and CO2, that water is actually gaseous. But in this instance, yes, this is like in a beaker, so we're not producing any heat. Or we'll produce some, but not enough to turn it gaseous. All right, so let's set up a mine table. Let's neutralize some stuff. I have 0.5 moles of my HClO, and I have 0.5 moles of my KOH. Water, we don't care. This other product is nothing until something happens. This is moles initial, right? Neutralization, acid, base. They neutralize and neutralize and neutralize until we've got nothing. They're both the same. What's going to happen? I have no leftover weak acid, and I have no leftover strong base. But I do have 0.5 ClO1 minus, hypochlorite. I want to solve for the pH, right? Okay, what do I have right now in my solution? Once I'm all done, what do I have? Well, I've got none of that. I've got none of this. All I have is this stuff. What's that stuff? It's hypochlorite. Acid or base? You wish.
Just tell us.
What's this? Strong or weak? Weak acid, right?
Weak acid.
What is this then? It's its conjugate base. Strong or weak? Weak. This is a weak conjugate base. This is not neutral. Why is it not neutral? Well, it's not neutral because it came from a weak substance. You remember when we did that whole salt thing, right? Yes, you do. When you analyze salt, you analyze the cation, you analyze the anion separately. If the cation of your salt came from a strong substance, the cation is neutral, right? If the anion of your salt came from a strong substance, the anion is neutral. This came from a weak acid. Therefore, this is also weak. This is a weak base. What we have right now is a weak base in solution. Is that going to mess with the pH? Yes. Yes, it will. This is not neutral. We can't just write 7 this time like we did for the previous problem. Why were we allowed to write 7.000? Because our ions that we had left over were neutral ions. We had a strong acid and a strong base. So what we were left with was nothing but neutral stuff. Now in this instance, we have equal acid and equal base, but what we're left with isn't neutral. So we've got to analyze it. We've got to figure it out. If this is a weak base, we have to set up an ice table to solve for how much hydroxide that weak base actually produces. Okay, so time out. Are you following my logic at the very least? I'm not saying you have to like it, but you see what I'm talking about, right? Okay, so now let's go through the motions. That was inconclusive, but I'm plowing forward. What we need is to analyze this weak base. In order to analyze the weak base, we're going to need an ice table. So let's show a chemical reaction proving that that stuff is actually a weak base. I'm going to have ClO 1 minus plus H2O liquid Why is that fact?
Because it's a reversible reaction.
Uh-huh. And weak acids and bases have reversible processes. Sorry, that's the inappropriate pronunciation. Processes with water. As the product here, I'm going to get, this is the acid now, it's going to donate, and I'm going to get HClO, AQ, and I'm going to get hydroxide. I know, right? Isn't that weird? Isn't that fun? What a great day to do this on.
I think all of our grades are like left at about 12 o'clock.
Mr. Bronte, Logan needs to know where the K went.
Yeah, where is it? Is it not KOH?
Disappeared.
It disappeared.
So, no, that's a fair question. So this is a strong base. Let me go all the way back. All the way back. When you have a, so this is like KOH in this problem, right?
Oh, it's the, okay, the ones that all cancel out at the very end.
Yeah. So I'm kind of skipping this thought process when we come across a strong acid or a strong base now. But this is what's happening. So KOH is strong, so it really looks like this. And when I neutralize this stuff, it just, the K gets crossed off. So all I really care about is the OH.
Okay, that actually makes sense.
You're welcome. Thanks for asking. Where was I? There I was. All right. What's my molarity of ClO1 minus? 0.5, because I was in 1 liter, right?
Yes.
And this was 0.5 moles, because this is a mine table, and those are moles.
Yes.
So are
That's
we
going to get annoying later, yes?
Are we using the values from the end of the line table or from like doing a whole new?
We are using the value, so this, okay, yeah, good question. Let me be a little more clear maybe. I had an acid, I had a base, and they reacted. After the neutralization, what I'm left with is nothing but weak base. Now the question is okay, well, how does that weak base affect the pH? In order to analyze our weak base, we need to set up an ice table to figure out what it's doing in the water.
Okay.
So it feels like we're kind of doing two things at once, or sorry, it feels like we're kind of going in sequence. This all would occur at the same time in the actual beaker, right? This equilibrium would start showing up the instant that we started to produce any of that product. But on paper, we kind of have to do it step by step.
Yeah.
So the first step was acid base react. And now we're at the end. What do we have left? We have weak base. Okay, let's analyze the weak base.
Got it. Thank you.
You're welcome. You know, in some interviews, that's a good thing. How much of this is going to break apart? Or how much of this is going to go away? Strong or weak?
We don't know this week.
We don't know. It's weak. I have no clue. We finished an ice table. What should we do now? Nice. I'm glad that's gotten settled in for you guys. K, what kind of K is this?
K.
What is that? That's a base. So what kind of K is this?
Hey, I need more space.
Sorry. I apologize.
Just extend your page.
That's my joke.
I got more left.
That's because no one likes it.
Wait, what? We just went to a really dark place. You need to talk to someone.
No, I'm okay. My wife's a psychologist.
I got fun.
It's okay.
Wait, Mr. Bronson, are you a Pisces?
Yes,
When were you born?
March 20th, isn't that Pisces?
Yeah.
No,
Go on, boys.
happy birthday.
Oh, yeah, that was last weekend. Thanks.
Oh my God.
You just
I'm sure I have a party or something.
Yeah, why didn't you tell anyone?
Oh my gosh, you should have made it.
I'm an old man. Birthdays aren't cool. I'm not 7,
You're not.
right? I don't know. Like, I'm sorry, I'm saying as an old man, birthdays are just irrelevant. I wish.
Still the day born.
Now, wait, yeah, we can. Way back up here.
That's the K value.
Please listen. Way back up top, I gave you a K value. What did I give you? KA. What are we solving for down here? Uh-oh. How do I get from KA to KB?
But do we know KW dub?
We do. That's a constant.
Oh, is that the?
Doesn't it literally tell us what KA is though?
Yeah, but we don't need KA. We need KB. We're looking at a base.
What?
Okay, so let's,
No, I don't.
In your formula packet, you have an equation that says KW equals KA times KB. And on that same line where KW starts, it says KW equals 1.0 times 10 to the negative 14. So let's convert our KA that was given to us into a KB. The KA that was given to us was for the weak acid. KA, how did that move? That was weird. Okay. This ain't gonna work. This Ka value is for the weak acid, yes?
Yes.
We're solving for the Kb of its conjugate base. Remember what I said the other day. I said that this equation only works if it's for a conjugate acid-base pair. We were given Ka of HClO. We want to solve for the Kb of ClO1 minus. This equation will work because we have a pair, acid-base pair. Kw is 1.00 times 10 to the negative 14. Ka is 3.5 times 10 to the negative 8. We want to solve for Kb. What do we get for a value of Kb? 10 to the negative 7. Can I chop this off one digit?
Oh, and G now. Girl, that's a 2.5.
So this goes over here. And now I want to solve for x. I don't like that. Thanks, Jacob. What did I just solve for?
Which is the pH, right, or we can use it for the OH, the OH times pH, right?
Correct. What do we get for a value of POH? 2.423. Whew. That was a lot of work. Good question.
Was Jerry.
No, it's a good question. That's Benton.
Or those two reactions, the second one is just the reverse of the first one, right?
Correct.
So then you can't take the inverse of the first one today.
So, couple things.
Yeah.
This in the forward direction is not the Ka value. Meaning, this is an acid-base reaction. Ka would be this reacting with water. So it's literally the reverse of what we're looking at. But in order to technically use this, I guess, well, yeah, this is the way. This is the way.
So the Ka you're saying is only for water.
Correct. It would be this acid with water or this acid dissociating all by itself. All right. Let me recap. That was a little extensive. We had an acid-base reaction. We had a weak acid and a strong base reacting with one another. The very first thing we wanted to do was figure out what is left over after they've neutralized each other. So we started with a Mine table. A Mine table is used for neutralization. We had 0.5 moles of the weak acid, we had 0.5 moles of the strong base, and we realized that they're going to fully neutralize each other to the point where at the end, I have no weak acid left over, I have no strong base left over. What I do have is conjugate acid produced as a result of that process. I have produced 0.5 moles of weak conjugate base. I'm sorry, did I say acid? I apologize. I produced 0.5 moles of weak conjugate base. This is the only thing in my solution at that point in time. And this will affect the pH. Because it's a weak base, we need to set up an ice table to solve for its pH. We set up the reaction of that weak base and water, and then we set up the ice table. This is molarity. I have no clue how much of this is going to break apart because it's weak. As a result, I use X. I set up my ice table, and then I set up K. This is Kb. The reason why it's Kb is because the substance we're trying to figure out or analyze is a base. As a result, we can set this up generically. We can plug in our X values from our ice table at the E, right? This is equilibrium. This is the equilibrium constant. So we use these values in that process. But then we needed the correct value of Kb to actually set this equal to. In the problem, they gave us Ka. That's for the acid. We don't have the acid HClO. We have its conjugate base, ClO1 minus. So we need to convert our Ka into Kb using this equation. Kw equals Ka times Kb. We solve for Kb. We set it equal to our K expression that we had set up earlier. And then we did the algebra, solve for X. When we got X, X was hydroxide. Negative log of hydroxide gives us POH. 14 minus that gives us pH. It was a doozy.
Wait, is POH just pH?
More or less, yeah. Good way to think about it. All right.
So, I'm sorry, I have a quick question.
Yeah.
When we're doing these like ones, does it start out with acid and strong base, or like reverse, like a strong acid and a base?
Yes.
And then it leads to only a certain amount being left and left the so it's not like it's weak acid and weak base being combined.
Correct. We're not doing that.
Okay.
We don't want to go there. If you don't like this, you're not going to like that.
Okay.
Yes. Oh, God, no. What I would like you to do, focus all of your brain power in the next 12 minutes. I know it is. See what you can do on number 10. Try. All I'm asking is that you try, because then you don't have to see me for a week. See what you can do.
He gave us notice.
Yeah.
What's the first thing you need to do? One person at a time. Shh. What is the very first? What is the very first thing we need to do? I don't hate that. Yeah, you can do that in your head. I want moles.
Wait, is there no name in the question?
Yeah, there is.
Oh, really?
Yeah.
Oh, shoot, I was gonna talk to you for a minute, that's so embarrassing. I'm sorry. Oh, no,
We want to get moles first. We need moles to put in the mind table. Moles to go on the mind table.
We haven't quite.
Yeah, they can't.
You could hypothetical thing in like up there. Oh, like you can't maybe. Oh. I thought you were talking about. Well, it's like.
It's just to show.
Yeah, exactly. So then there has to be a and how it goes. Sure. When you get to lay down. Yeah, about how much, how many years old for the you want that thing? Because the stairs might slow down. Yeah, I like watching. Well, I'm you don't even, people are so bad at playing.
Watch that. Appreciate your No, no, I'm done. I appreciate Yeah, you didn't know.
Okay, give me a couple minutes of your attention. We are mixing a strong acid and a weak base. When we do this, we would like to set up a mine table to show the neutralization. Before we can do that, we need to solve for moles of both our acid and our base. Because our acid is strong, we would like to solve for moles of H1 plus. Because our base is weak, we can just solve for moles of whatever it is. I have a volume of each, I have a molarity of each, and I'm going to convert all of this into moles. When I do that, I realize that I have equal moles strong acid and equal moles weak base. I set up my mine table. The reaction is this format. I don't need HI because this is a strong acid and it's going to dissociate. The iodide ends up being a spectator ion. Again, whenever you have something strong, acid or base, if it's a strong acid, you just need to write down H plus for that strong acid. If it's a strong base, you just need to write down OH1 minus for that strong base. Whatever other ion is with it is neutral and it's irrelevant. So I have strong acid, I have weak base. They react Bronsted-Lowry style. This will donate, and I end up with ammonium. I have 0.4 moles of each. I set this whole thing up, and what do I get when it's all done? 0.4 moles of this. What is that? It's ammonium. Acid or base?
Acid.
What is this?
Acid. Base.
This is a weak base. This is a weak base. Therefore, this is its conjugate acid. If this is weak, what is this? Also weak. Meaning, we have nothing but weak acid in our solution. Bring it.
Go on.
They don't need help getting distracted today, Grosh.
Oh, yeah. Okay. My bad.
No, you're good. We have nothing but a weak acid in our solution. So how are we going to solve for the pH? Ice table.
Yeah, I got there before you.
We need an ice table. However, if you got this far, you probably screwed something up. Because in our mine table, what value is that? 0.4 what? Moles. And when I go to the ice table, it needs to be molarity. So I should totally take that quantity of moles and divide it by the total quantity of volume, which is 0.6 liters.
I was so excited.
I know you were. I'm sorry. Smashed your hopes and dreams right at the end. People online, have a lovely day. Thank you for joining me. Enjoy your break. People in front of my face, please sanitize. We'll have some fun after break.
I
dropped that. I'm going to go down 10.